हेलो गाइज, वेलकम बैक टू माय यूट्यूब चैनल। तो गाइज लास्ट वीडियो में हमने क्या देखा था, आइडियल मॉसफेट को हमने देखा था, राइट। एंड वो मॉडल यहाँ पे आपको दिख रहा होगा स्क्रीन पे। सो दिस मॉडल को हमने डिस्क्राइब किया था एंड उसके साथ ही हमने फिर लास्ट में कुछ जीएम के डिफरेंट फॉर्म्स को देखे थे। ओके, नाउ इस वीडियो में हम लोग क्या देखेंगे, विल सी मॉडल्स फॉर एनालॉग डिजाइन इंक्लूडिंग चैनल लेंथ मॉड्यूलेशन एंड बॉडी इफेक्ट। तो लास्ट वीडियो में हमने ये सब कवर नहीं किया था, हमने बस क्या किस चीज़ को कवर किया था कि ट्रांस कंडक्टेंस को, जीएम वैल्यू को, ठीक है। तो उससे हमने कंस्ट्रक्ट किया था एक आइडियल मॉसफेट का मॉडल। अभी हम क्या करेंगे इस लेक्चर में, इसमें हम देखेंगे कि अगर चैनल लेंथ मॉड्यूलेशन जो लैम्डा कोएफिशिएंट होता है उसको भी इन्वॉल्व करें एंड बॉडी इफेक्ट कोएफिशिएंट को भी हम लोग इन्वॉल्व करें, तो जो ये मॉसफेट मॉडल है वो अकॉर्डिंगली कैसे चेंज होता है, राइट। सो जल्दी से स्टार्ट करते हैं। सो लेट अस सी फर्स्ट ऑफ ऑल व्हाट विल सी विद रिस्पेक्ट टू चैनल लेंथ मॉड्यूलेशन। ओके, और उसके लिए हम लोग क्या करेंगे, उसके लिए फर्स्ट ऑफ ऑल व्हाट विल डू इज लेट अस ट्राई टू डू, एंड लास्ट लेक्चर में हमने क्या देखा था, सबसे पहले इफ यू रिमेंबर हमने ऐसा बोला था कि नाउ देयर आर टू वोल्टेजेस, एक तो लैटरल वोल्टेज एंड द वर्टिकल वोल्टेज रेस्पॉन्सिबल फॉर द करंट आईडी। सो दैट इज वीजीएस एंड वीडीएस रेस्पेक्टिवली, राइट। तो वीजीएस को हम वेरी करेंगे और वीडीएस को कांस्टेंट रखेंगे, तो ये हमने लास्ट वीडियो में देखा था, राइट। सो इफ यू रिमेंबर आई सेड हम लोग टू केसेस देखेंगे। सो दिस इज आवर केस नंबर 1, राइट। हमने क्या किया था, वेरिएशन ऑफ आईडी विद रिस्पेक्ट टू वीजीएस। तो वीजीएस को वेरी किया था जबकि वीडीएस को कांस्टेंट रखा था, राइट। एंड वीजीएस को कैसे वेरी किया था, कुछ डीसी पोटेंशियल दिया था एंड सम एसी सोर्स दिया था विच इज द एक्चुअल सिग्नल गोइंग टू वेरी, जिसे आपको एम्पलीफाई करना होगा, राइट। तो इस तरीके से हमने वीडीएस को कांस्टेंट रखे, यानी कि सुपर पोजिशन का बेसिकली यूज करना है, एक को कांस्टेंट रखो दूसरे को वेरी करो। नाउ इन द सेकंड केस अब मैं देखूंगा आईडी विद रिस्पेक्ट टू वीडीएस व्हाइल कीपिंग वीजीएस कांस्टेंट। ओके, सो नाउ लेट अस सी दिस. So now in this case the second case will be our variation of ID, current ID, variation of ID with respect to what, VDS. Okay, so let us draw the circuit first. So this is your MOSFET. Now this time your VGS will be constant, so I'm giving a DC voltage and let us call this as VGS, and here you will have your VDS voltage required for biasing, and यहीं पे आपको क्या करना है, अब एक AC source देना है, basically varying source VDS. So which means you are now varying your VDS. Okay, so what will happen due to this, there will be current flowing in this from drain. We will call this as ID plus small id. So this capital ID is the DC current, whereas small id is the AC current, okay, flowing through this MOSFET. Now isko analyze karenge, so and we'll consider the non ideality case, that is the CLM is included. So we'll consider our non ideality parameter CLM, channel length modulation, already पता होगा, जिन्हें नहीं पता होगा, like simplify to describe it now, CLM means when VDS increases continuously, आप VDS को increase करते रहते हो, so what happens is basically आपका जो channel है वो from the drain side actually ये deplete हो जाता है, right, pinch off हो जाता है, but as you keep on increasing VDS continuously, electric field जो है through from the drain side increases, which actually pulls the electrons from the source, तो उसकी वजह से थोड़ा सा there is increase in the current from the drain side. So that's why we say that there is slight increase in the current even in saturation region. So let me actually draw this so it will be more clear to you, right. So let us see here. Okay, so now what we'll do is, so ideally क्या होता है कि आपका करंट कुछ इस तरीके से होता है in saturation region, but मैंने क्या कहा, this is what curve ID versus VDS, but this is without CLM. Okay, I write here without CLM, and how it will be with CLM. Now in saturation region as VDS continuously to increase, यहाँ से देखो VDS increase हो रहा है, so electric field increase and there is some pull from the source for electrons, ठीक है। उसकी वजह से क्या होता है, there is some slight increase. अब ये constant नहीं रहेगा, अभी तक जो आप यहाँ पे constant current देख रहे हो ID, there is some small increase. So now let us represent that small increase. तो यहाँ तक you can say it's going the same, and then what happens is just like this. So this is the current with CLM. channel length modulation. So this is called the CLM effect. Okay, slight increase in the current. So now आप देखो current constant नहीं है, but there is small increase, although it's not that increase जैसा आप linear region में देख रहे हो, but there is still some increase in the current that is very minute. So this effect is called the CLM effect. तो हम इस parameter को भी consider कर रहे हैं, and it is represented by the parameter lambda. So we say CLM coefficient is given by lambda. Okay, so now what you see, let us go back to the MOSFET model. Now you see the current जो यहाँ पे current flow हो रहा है ID, that will be some transconductance value G naught times VDS. Okay, like the same जैसे हमने यहाँ पे बोला था, current ID will be GM times VGS. So we knew the transconductance value like GM. So what is GM? Transconductance is the strength of MOSFET, right? हमने बोला GM को कैसे define किया था? Basically a MOSFET is what? It converts voltage into current. So how strong a MOSFET is, it is defined by the parameter GM. तो कौन MOSFET कितने करंट को कितने वोल्टेज में कन्वर्ट कर पाता है, तो that strength can be defined by GM. So GM का unit is, I will write here, GM का unit is ampere per volt. Usually we represent it in milliampere per volt. So that means for 1 volt, of if some MOSFET can convert it to 10 milliamperes, and while there is some another MOSFET, if you provide 1 volt and it converts to 100 milliampere current, so definitely you will say the GM of second MOSFET is better. That is, the second MOSFET has greater strength as उसी same voltage को ये 10 times ज़्यादा magnify कर रहा है than this. So that's how GM is defined. Okay, now on the same pattern यहाँ पे भी हमने current ID को G naught times VDS से represent किया. Okay, now what happens is so you write the current equation here. So ID is half of mu n COX W by L VGS minus VT whole square. Already we know that it is operating in saturation region, because for amplifiers already discussed कि आपको saturation region में ही रखना है, ठीक है, तो तभी it will work in saturation, as an amplifier. Now and why that? Because हमें चाहिए एक constant current source, and constant current source कहाँ पे possible है? When it is in saturation region. Now but एक और चीज़ जो हमने यहाँ पे बोला कि we are including the channel length modulation, तो उसकी वजह से slightly there will be change in this current equation. So it will be represented by, there will be extra term of 1 plus lambda delta VDS. That is the change in VDS. So this total equation will be with CLM. So if you multiply this, if you only write this, it is without CLM. So आप देखो without CLM there is no dependence on VDS, but if you consider CLM effect, then there is a dependence on VDS. Okay, there is a change, that is, it is proportional now to VDS. That's what I said. If VDS increases, electric field increases. So once CLM comes into the picture, उस time पे आपको VDS को भी consider करना है. So now because we are saying that we are including the channel length modulation, so we'll include this term also. Now what we'll do is we can also write now it as therefore ID is equal to ID saturation, ID sat, because this current we know now is the normal saturation current, and what is extra now? 1 plus lambda of, and suppose let us call this delta VDS, so we can write as some VDS minus VD sat. This VD sat is the minimum voltage required for saturation. Suppose like this point, this is your VD sat here. So the voltage where the MOSFET enters to the saturation region, and उसके बाद आप जितनी भी change करोगे, now some small VDS is here, so this is that delta VDS. So I have just explained this delta VDS को break down किया, and VDS minus VD sat. Okay, so now you have the current. Now what is your this G naught? It can be defined as delta ID by delta VDS, right? G naught is what? As I mentioned, G naught is your transconductance. That means current by change in current with respect to the voltage. So change in current ID with respect to the what is the varying parameter here, VDS. So मैंने G naught को कुछ इस तरीके से define किया. So what you do the differentiation, partial differentiation of ID by VDS इस equation में. So what it becomes? Let me change the color. So ID sat is constant. It will be as it is. Now 1 का differentiation will be 0. Again VDS का, let me write it here, 0 plus lambda. For VDS what it will be? Again 1 minus, this is a constant, so 0. So what it comes out to be? ID sat times lambda. So this is your G naught, right? This is your G naught, transconductance. Now that you have seen this is your transconductance, we can also from this equation only we can say that your R naught, basically the resistance, will be now equal to the reciprocal of this transconductance, that is 1 by lambda of ID sat. Okay, so this is how we define it. Sorry. So this is your what is called as output, small signal output resistance. Small signal output resistance. Okay, so this is called as small signal output resistance. I hope this is clear. Okay, now what we'll do this, अब हम फिर से मॉडल करेंगे अपने जो हमने आइडियल मॉसफेट मॉडल डिराइव किया था, तो उसमें अब इस चेंज को रिप्रेजेंट करेंगे. अभी तक अगर आप देखो, दिस वाज द मॉडल, राइट? सो इफ आई कैन जस्ट कॉपी इट देयर. So let me copy it to the next page actually. Yeah, so this is the model. Okay, now इसी मॉडल में आप देखो there will be a now change, right? So let me actually grab it to the center like here. Yeah, this is fine. Okay, so what we are saying, this was our ideal MOSFET का model. Now the change what we just now produce is if there is now CLM effect. Okay, if there is now CLM effect, we saw that output resistance R naught will be equal to the what? 1 by lambda times ID sat. And what is this lambda? This is the CLM parameter. Okay, and its unit is 1 by volt, that is volt inverse. Okay, so lambda unit is volt inverse. Now we will try to model this CLM parameter into this model. So what happens here is ID was till now equal to GM VGS, but just now we saw now ID is also equal to your G0 VDS. So if you apply both, that means you are changing your VGS also and VDS also. तो अभी तक तो हमने इंडिविजुअली देखा था, एक को कांस्टेंट करके दूसरे को चेंज किया था, बट अब मैं बोल रहा हूँ कि अब लेट्स गिव बोथ, लाइक द चेंजेस इन बोथ. VGS is also varying, VDS is also varying. Now this G0 VDS also comes into the picture. Now this ID here which was flowing through this is not only equal to the GM VGS, but also now what extra will be there? There will be this extra current source which I may have to put here. That will be equal to what? G0 VDS. Okay, so that will be now equal to G0 VDS. So what I'll do here also, I'll remove this ID here because now this is no ID. Okay, so this is simply your GM VGS, right? So this is simply your GM VGS. So this value is your GM VGS. Okay, now where is the ID then? Here. The total ID will be now GM VGS plus G0 VDS because we are taking the parameter CLM and effect. Now there is one interesting C to observe here. यहाँ पे देखो क्या हो रहा है. This is your gate. Already I have mentioned gate, drain and source. If you see here, this is your gate, this is your drain, and then this is your source. Now you see what interesting thing is here. In case of GM VGS में आप देखो, जब मैंने current को सिर्फ GM VGS लिखा था, उस time VGS this voltage, I said this is voltage dependent current source, right? Voltage controlled current source. So where is the this is the current source and it is voltage dependent VGS, and that VGS is given here, right? So now in this case, इस case को आप देखो, there is again a current source, this is a current source, and there is a voltage dependency VDS. But ये VDS कहाँ पे दिया हुआ है? अगर आप देखो, this is the drain and this is the source. So this means this part is source. So VDS is itself this voltage, right? So between the ends of the current source, the voltage supplied is actually the voltage which it is dependent on. बात समझ आ रही? यहाँ पे देखो, in this case जो GM VGS जब मैंने कहा था वोल्टेज डिपेंडेंसी है, तो वो किस वोल्टेज पे डिपेंड कर रहा है? जो कि कहीं दूर जाके है, कहीं अलग सर्किटरी में है, कहीं एक VGS वोल्टेज सोर्स है, उस पे डिपेंड कर रहा है उसका करंट, राइट? सो एज VGS चेंजेस, इंक्रीज डिक्रीज, उसी हिसाब से ये करंट भी यहाँ पे इंक्रीज या डिक्रीज हो जाएगा. सो डिपेंडेंसी इज समवेयर एल्स, करंट सोर्स इज समवेयर एल्स. दैट्स माय पॉइंट. बट इस करंट सोर्स के लिए अगर आप देखो, द VDS जिस पे डिपेंड कर रहा है वो इसी के अक्रॉस है, इसी टर्मिनल्स के अक्रॉस हमने वो VDS को दिया है. सो नाउ बेस्ड ऑन दिस ऑब्जर्वेशन, so any change in this VDS, that will be the linear change, and that linear change can be modeled by a resistor. So you have to understand my point. So what I'm saying here, यहाँ पे आप देखो, now this, if I take it separately here, this is your drain, this is your source, and this is dependent on G0 times VDS. So any change in VDS is the change across its terminal, which is this VDS. So it can be modeled, I can say it can be modeled by a simple linear resistor, which can be called by R0. So what I can say, linear change in VDS can be modeled by resistor. Okay, so this is the point, this is the key to observe here. आई होप आपको समझ आ रहा हो वाई रेजिस्टर से, क्योंकि रेजिस्टर में लीनियर चेंज होता है, राइट. ओम्स लॉ, एज वोल्टेज इंक्रीजेस योर करंट इंक्रीजेस, एंड देन फॉर द प्रोपोर्शनैलिटी व्हाट यू डू, V by I इज ऑलवेज कांस्टेंट इक्वल टू R, सम रेजिस्टेंस R. सो सेम थिंग इज हियर. यहाँ पे आप देखो दिस करंट सोर्स, ये करंट बढ़ेगा जब इसके अक्रॉस का वोल्टेज बढ़ेगा. सो isn't that the same what Ohm's law is, and isn't that the same what a resistor represents, that is the V by I is constant, and that a change is represented by that constant is represented by your resistor. So same thing we are modeling here. So instead of using now this G naught VDS, our model, how it changes, so let me draw a new model now here. So this model changes now accordingly, and we can say the same, this gate terminal, this plus minus VGS, this is your source. Now what you had, GM VGS here, and now instead of the current source I'll model it using a resistor. So this is your resistor R0, and now this is your drain terminal, right. So this is the model which includes the channel length modulation, not body effect. So the topic is channel length modulation and body effect. So far we are just focused on CLM parameter. So once this lambda comes into the picture, what we'll see is there comes this R0, and now we had derived this R0 here is our R0 equals to 1 by lambda times ID sat. Now what is the thing here, if we go again back, what we're seeing is R0 is your 1 by lambda times ID sat, right. So if you are including the channel, this CLM parameter, suppose if you are not including, first let us take the case of not including. Suppose case 1 is if you are not including CLM parameter, that is lambda is 0, at that time your R0 will be infinity. So R0 infinity means open circuit, so you don't have to use this R0 actually, so you can just leave that open, so it will be an open circuit, no R0. But if some finite value is given, that is non-zero value, so then R0 will be equal to what, 1 by lambda times ID sat. Okay, so that time you need to make sure that you include this R0 parameter in the model, otherwise the model reduces to the what is called as ideal MOSFET model, which was studied earlier, this model right here, right. So in this you can say this is which model, ideal MOSFET model. So in this case our lambda is 0, so that's why R0 becomes infinity, that means that is open circuit here, like this open circuit. So we don't show R0 here. So this is the case where CLM is introduced, and at what condition, when lambda is given some finite value. Suppose in a problem if it is given lambda is non-zero, then again you don't need to consider this R0. Okay, I think that's clear. So now we'll move on to our second effect, which is called as body effect. Okay, so we'll move. Okay, let us do now the third case, which is variation of ID with respect to VSB. Okay, with respect to VSB, what is VSB? The source to body terminal, the source to body potential. Okay, now let us again make a diagram and see the effect. Okay, I hope this is clear. So this is my MOSFET. So VGS, I'm giving a constant supply DC voltage VGS, and now VDS also here I'm giving a constant supply. Now what is varying is the body terminal. Okay, so let me ground this. So where we show body terminal here. Okay, so this is your body terminal, and now I'm giving some VSB here, and now again what I need to do is connect some AC source at VSB. So to vary VSB, basically all other are constants DC voltage, and what I am varying here, because we need to study variation now with respect to VSB. So wherever you give variation, at that point you have to connect the AC source. So like in the previous case where VDS was varying, so we connected a VDS here, right. So in the same first case we can see VGS was varying, so we connected AC source. So yeah, I think that's pretty clear. Now what happens here, now let me again write the current flow here. Let me write the current flow here, small id plus capital ID, right, the DC current plus the AC current. So now you can write the drain current as again half of mu n cox W by L VGS minus VT whole square, right? Just like the same. So now as we mentioned here, right, 1 by 2 mu 1 CX W by L VG minus VT whole square. Now what you do here, for VSB, what we'll do is first we'll calculate the threshold voltage, this VT, okay, this VT. If you had studied digital electronics, digital IC design, you must have heard about this formula. VT is given by the VT naught, which is the nominal threshold voltage, and plus this body quotient gamma. This is called the body coefficient, okay, body effect coefficient. So root under minus mod of minus 2 phi f, which is the Fermi potential, plus VSB mod close, then minus root under mod of minus 2 phi f. Okay, this is the formula. So what is this here? This is the nominal threshold voltage if gamma is 0. Nominal threshold, I will say nominal VT. So see, if gamma is 0, then this VT becomes VT naught. And what is this here? This is the body effect quotient. That means if body effect exists, we have to use this quotient, okay, body effect coefficient. Now what you will see here, and this phi f I said already is Fermi potential. Again, the use is not here कि ये formula कहाँ से आया. This is already इस course के लिए ये ज़रूरत नहीं है. It's like not a part of this course. But again, I will suggest अगर किसी को जानना है इसके बारे में doubt है, so they refer the digital IC design का course. So in that you will get the idea of how this is. So basically this maps that when your VSB, this source to body terminal, as now you see what happens here, as I'll say VSB increases, okay, this VSB increase, what happens is this VT also increases, so the threshold voltage increases. And what happens if threshold voltage increases, right? What will happen to the drain current? So suppose, what is threshold voltage basically? जहाँ पे आपका करंट फ्लो होना चालू होता है, राइट, बेसिकली व्हेन VGS इज ग्रेटर देन VT, तभी आपका मॉसफेट ऑन हो जाएगा. अगर तभी आपका मॉसफेट में चैनल फॉर्म होगा. सो एक बार चैनल फॉर्म हो गया, देन आपका करंट भी फ्लो हो सकता है व्हेन यू अप्लाई द VDS. बट इफ आपका चैनल ही फॉर्म नहीं हुआ, इफ द गिवन VGS लेस देन VT, वी नो द कंडीशन, इफ VGS इज लेस देन VT, whatever you do with the VDS, there will be no current because channel ही form नहीं हुआ है. See, this is the effect of the horizontal voltage, which the vertical voltage, जो हमने पहले लेक्चर में देखा था. तो यहाँ पे ज़रूरी है, और हाँ, किसी को कोई भी डाउट्स आया है तो प्लेलिस्ट में है, पूरी लिंक्स के डिस्क्रिप्शन है in the description, तो आप जाके चेकआउट कर लो लिंक्स को. सो ऑल द वीडियोज आर इन द प्लेलिस्ट. ओके, नाउ अगर VGS जो है लेस देन है VT, मेरा मॉसफेट ही ऑन नहीं हो जाएगा, इट विल बी ऑफ. एंड नाउ यू सी, मैं अब क्या हो रहा है, इस VSB को इंक्रीज करने से VT इंक्रीज हो रहा है. दैट मीन्स नाउ यू रिक्वायर मोर VGS टू एक्चुअली टर्न ऑन द मॉसफेट. अगर अभी तक VT का वैल्यू कुछ था, सपोज 0.6 वोल्ट्स, नाउ VT इंक्रीज होके 0.8 हो गया. ओके, नाउ यू नीड VGS at least 0.8 volts to form the channel, to invert the channel, right? तब तक आपका VDS कुछ भी हो, the current won't be there. So that means actually what is happening, my current is decreasing, ID current is decreasing, right? So that is the effect of VSB. If VSB is increasing, because threshold voltage increase हुआ, उसकी वजह से जो drain current पे जो relation आया, effect आया, वो decrease हो जाएगा ultimately. Okay, so if you have to see the graph also, the graph of this will look somewhat like this between VT and VT naught, actually VT and VSB. So if I have to show like this, so this is your VT and this is your VSB. And at suppose if your this VSB is 0, what happens is, suppose VSB is 0, आप यहाँ पे VSB को 0 put करो, this will become 2 root of 2 phi f and minus root of 2 phi f. So again it will become 0. So this whole thing will become 0. VT will be equal to some VT naught. So if your VSB is 0, now if VSB starts to increase, what will happen? Your VT will start to increase. So like this relation is there between the VT and VSB. And same thing, once VT increases, current decreases. Okay, now you got that. So now this is also called as the back gate. Now this body terminal is also called back gate. Back gate क्यों? देखो, जो normal gate होता है आपका, so let me actually show it here. If जो normal gate है, VGS gate, if that voltage increases, क्या होता है उससे? Current ID increase होता है, right? We know this. क्योंकि the inversion layer will be created more rapidly and henceforth the current will increase. But वहीं पे आप देखो अगर इसके opposite होता that is the VSB is increasing, आप देखो क्या हो रहा है, ID decrease हो रहा है. That means it acts as a back gate. So body is acting as a back gate. So that is meaning simply इनवर्ट ऑफ गेट. जो गेट काम करता है उसका उल्टा बॉडी काम करता है. गेट काम करता है आईडी को बढ़ाने का, while as this back gate काम करता है आईडी को घटाने का. So this is what I mean. So now again if we have to model it, again what we'll do, we'll call a term transconductance GMB, that is the GM of body. Again it will be represented by delta of ID by delta of VSB, right, at some VSB. So this is how we'll represent it, and how the graph will look like. Let me again draw graph so it will be clear. Yeah, so this is the graph of what, ID versus VSB. And how it looks like, I said as VSB increases आपका जो current है वो decrease होता है. So it goes like this. Okay, so it is like this. So this is the ID versus VSB का curve. Now what is your GMB? Delta ID by delta VSB. Okay, so the slope of this graph at some potential VSB. Suppose you are giving this DC potential VSB, इस पे जो change होगा, so that is your GMB. Now again we'll use the formula and we'll calculate. Let me go to the next page actually. So now what you will do, let me actually copy this, right? Yeah. So this was my, suppose, let me do it actually like this. Suppose you are giving some VSB here, like this, AC. So this will be your variation in ID versus VSB. Okay, so my drawing is pretty bad, but yeah, you can understand. Now what happens is we need to calculate this GMB value. Okay, GMB value. So again we'll use the formula of ID. This where is ID? This equation. Let me also copy it there. This is the ID equation, and now what happens, we'll just calculate our GMB. So GMB is delta ID by delta VSB. So you do this. So what happens, 1 by 2 mu n COX W by L. So it will be twice of VGS minus VT into what? Because see, what is the variable here? VT. Why VT? Because once your differentiation with respect to VSB, we know VSB is actually dependent on VT. So that's what I was telling. VSB is dependent on VT. So you have to consider that equation. You can't simply say that delta IB by delta VSB is 0 because there is no VSB in this. No, VSB is actually, it depends on VT. Na? So that means there is a variable, there is a dependency. So VT here is actually dependent on VSB. So using this formula, right? So let me also grab this formula from here. Let me keep it somewhere here. Yeah, we actually do it a little. Yeah, this is fine. So now you see there is a dependency of VT on VSB, right? VT is dependent on this VSB, as you can see. So that's why I'm differentiating with respect to VSB. So I'm making this as variable. So 2 comes down, VGS minus VT, and delta minus of delta times VT by VSB, delta VSB. So this is how we do differentiation. Now this is the internal differentiation of VT with respect to VSB. Now you have done this. Now come to this. Now we need this term delta VT by VSB. So what you will do? Now you differentiate this VT by VSB. Okay. So delta VT by delta VSB will come from this equation, and VT is constant. It will be 0. Then gamma is here. So into root under what it will be, 1 by twice of root under minus 2 phi f plus VSB. Okay, again 2 phi f is constant, so it will be 0. So this will be the total differentiation. Now you put this, let me call this equation 1 and this as equation 2. Now you put the equation 2 in 1, so put 2 in 1. So you put this value here, so GMB will be how much? Delta ID by delta VSB equal to, so 2 and 2 will cancel out, mu n COX W by L VGS minus VT, and you put the substitute the formula of this, so minus of gamma by 2 root under minus 2 phi f plus VSB. Okay, clear? So now what happens again, if you see at this term, what is this GM, this mu n COX W by VGS minus VT, it's nothing but GM, right? So if you remember from this past discussion, so you can see the first formula of GM itself is mu n COX W by L VGS minus VT. So we can call this here. So what we'll do now, your GMB is equal to GM because of this, and minus gamma of twice minus 2 phi f plus VSB. So this will become the formula. Now what you do is you represent all this thing with some term called as eta. So GMB will be minus neta times GM. Okay, so this is how we represent this, all gamma, this quotient gamma by 2, this we are represented by eta. So now what you see here is what is remained here. So eta is actually minus GMB by GM. Okay, so this is the formula you have to like keep in mind. Okay, so let me just write this here. Yeah, this is your GMB. Now what you see here is that this usually this eta is of the range of from 0.2 to 0.4. Okay, because again here if you see GMB is pretty less than your GM. GMB is actually less than GM, so that's why the ratio is in less than 1. 0.2 to 0.4 is the range. Okay, so this is a relation between GMB and GM. Now again, why we studied this, we actually now further want to improve the model. Further we are trying to improve the models considering the parameters. First it was ideal model, then we introduced CLM का parameter and modeled into a resistor. So now you see this model, हमने इसको resistor में model किया. Now same thing, now saying variation is with respect to VSB also. Now again this model we have to represent. Okay, so this change if we have to represent, what we'll do, so now we'll consider the final model, small signal model. So let us try to derive the final small signal equivalent. So now what happens in this, so there is this gate terminal plus minus VGS, this is your source, and now this we know GM VGS is there, then again G0 VDS which is modeled as a resistor is there. Okay, and now what is there further? Further will be there additional thing, this GMB VBS. Okay, and this body terminal is somewhere here. Suppose if it is connected to ground, so I can write whatever it is connected to potential, or suppose this is the body terminal, so this is your GMB VBS. So this is your drain here, source, and yeah, now this is the total ID current. Now what is the ID current equal to? So if you have to write it, so you can say now total ID current in the final small signal equivalent will be GM VGS plus VDS by R0 plus GMB VBS. So this will be your final equivalent. So now in this case, again, if it is given case 1, like if it is given like your this body coefficient, body effect coefficient gamma is 0, then again your GMB will be 0. Then you don't have to include this GMB. But if it is given some finite value, then only you have to consider this model GMB. Okay, then you have to include GMB. So there is a condition on these two now. So R0 and GM, this is GMB here. So R0 and for these two things to be modeled, there is a condition. For this thing is that lambda should exist. Lambda should be non-zero. And for this thing to be embedded in this model, द कंडीशन इज दैट द बॉडी इफेक्ट कोएफिशिएंट लैम्डा शुड बी नॉन जीरो। तो इसका क्या मतलब हुआ कि अगर आपको कोई क्वेश्चन दिया है जिसमें लैम्डा जीरो है, गामा जीरो है, देन व्हाट मॉडल यू नीड टू यूज, सिंपल आपको अपने मॉडल को यहां तक रेस्ट्रिक्ट करना है, इतना सा, ठीक है। अगेन देन इफ इट इज गिवन दैट लैम्डा इज नॉन जीरो बट गामा इज जीरो, देन दिस मच। एंड अगर दिया हुआ है कि लैम्डा इज जीरो बट गामा इज नॉन जीरो, देन आपको ये और ये लेना है, not r naught. So if it is given lambda and gamma both are non-zero, then तीनों लेने हैं. So based on the description given in the question, आपको अपने हिसाब से conditions apply करने हैं. But what remains constant is this, इतना तो हमेशा रहेगा, and based on these values, lambda non-zero और gamma non-zero, उस हिसाब से आपको इनको भी include करना रहेगा. So I think that the last small signal equivalent is now clear to you, and I hope कोई doubt नहीं हो. So कोई भी doubt हो comment section में बताना, and I think कोई भी चीज़ miss नहीं हुई इसमें. Yeah, I think that will be it for the today's lecture. So keep supporting guys, and do watch the other videos in the playlist. Thank you guys, and I'll see you the next time.